Okay, so in this video clip, I'm going to take a look at the Tian 1993 model again, and the binomial approach or the binomial lattice valuation approach uses this type of binomial tree in order to price options. And we explored that a little bit in this 2020 paper for the Journal of Futures Markets. And Tian, it's very closely related to Cox-Ross-Rubinstein, but under some circumstances, Tian 1993, its performance relative to Cox-Ross-Rubinstein can be a bit better. And likewise, Leisen and Reimer as well. But for the moment, I'm just looking at Tian. I previously looked at R code for Tian. I've left the links there below this video clip. I leave links to the R code. I've left links here. I will leave links to the Matlab code for running the same estimation. And we can have a look at the valuation here, the values that are revealed in these estimations. But very specifically for this video clip, I'm going to look at a Python implementation of the model using the approach, the NumPy library, set out by Cantarutti 86 financial model. So if you follow this link, you'll find he had set out this approach that I'm going to use here, but I introduced the Tian parameters. And in addition, I make some small changes. I think the biggest change here was 1 over D, which is not quite the same as the original code. Okay. So, okay, to get the ball rolling, keep in mind this is a Google Colab. I executed R code, Matlab code. I got some results for these parameter values. So we're going to use the stock price 100, exercise 100, risk-free rate 3%, sigma, or the volatility of the underlying asset return is 20%. The maturity of the option is 3 years. We're going to use a 500-step tree. The option is a call option. It is an early exercise, meaning American. And using the Matlab code that I did in the previous video clip, we got a result of 9.0638. Here, using NumPy libraries, NumPy, if set up and optimized, they can really be high performance. This is one of the attractions of using this specific approach as suggested by Cantarutti. Maybe we'll just take a look at that particular GitHub for a moment so that you can follow the source here. So I'll just come and paste it into the browser and take a look at the GitHub. So this is the GitHub, and it's Nicola Cantarutti, and he has a lot of really excellent stuff here. So I recommend this GitHub, even if you're not specifically interested in binomial trees. We are. And then he presented a binomial tree below here, simple enough type of construction. We make some minor modifications relating to the parameter inputs, and also down here, I make a small change to the code so that the Tian model will work, and estimate correctly. Okay, so let's take a look at that. We run these, introduce into this Python notebook the parameter inputs. Again, the values are the same as those that we had looked at for R and for Matlab, which I've completed above, and I will leave the link to this Colab below the video clip. We'll import the NumPy library. I've given a little bit of discussion around the NumPy library here, why it's important for fast estimation and how you can optimize Python code to be quite high performance, normally viewed as being a bit sluggish, but actually in this domain of binomial pricing, using NumPy actually has quite a significant bearing. And then the particular construction that Nicola has introduced here is also very important. And Okay, so we executed that and we're getting a value of 9.0638, which seems to tally with the result they have here for Matlab. And it seems to tally also with the result I had from the R code previously using those parameter inputs. If you look at the parameter inputs, these are the values I obtained here. And those results tally. Also, it might be worth noting the true value using a 15,000 step tree here is 9.066. So we're relatively close to true. We can go back here to our Colab NumPy implementation based on Nicola's approach, and we'll just make one small change here. Let's increase the number of steps from 500 to 15,000 and just see how quickly the code estimates. Normally, it actually is quite fast. So I'll run through that again. And then the final part to output fee, right? And you can see it estimates really quickly, right? And that's one of the attractive features of this particular format, this particular template. So I strongly advise go take a look at the Nicola Cantarutti GitHub. There's a lot of very nice material in there, very well presented, and in fact, a lot of explanation as well, which is also a very attractive feature of this. You have the Longstaff-Schwartz method for valuing American options, perpetual puts. So again, I recommend people take a look there. Okay, let's leave it there.